Hello everybody, this is Hansen and this is the first video of the real analysis playlist. So in this video, I'm going to convince you why the real analysis is important and why do we study it. And I'm going to give you some basic concepts like the definition of rational numbers and why the rational numbers system is not enough for our general purposes in mathematics. So the reason we want to study, so first of all, I think we need to understand what the real analysis does. And the real analysis is basically the study of the reals, of the real numbers. And you guys may wonder that, well, I know about real numbers already because we have been doing all the real number stuff in high school. But it turns out that the definition from high school is not quite precise. So um, the original definition of the real number is the union of rational numbers and irrational numbers. However, if we use that definition, we're not able to define irrationals precisely because when someone asks you about irrationals, we can only say that, well, it's just some real numbers which is not rational. And that's like a circular definition. So this is not super precise. And also, the real numbers system has some very decent properties. So for example, in high schools, we just write radical 2, and we assume that this is a real number. And without even checking whether this number exists, because we don't know that, for example, x squared equals to 2 has a well-defined solution. If I only want to check in the rational number system, which I'm going to denote by q, it turns out that this function, this equation doesn't have a solution in q because this function doesn't have any rational solutions. And that's why we want to extend our system to be a more complete and basically a better system which doesn't have any gaps, which is the real numbers. So basically a real number, a real system, it's a better system. And my goal, I'll say at least my first goal in this course is to start from the basics and we will construct the system together. So that would be the main idea of the first, I believe, the first 14 videos about the construction of the reals and the precise definition. Okay, so today it's going to be the introduction of rational numbers and many definitions. Okay, so, and also just to emphasize that for the source, we're going to use Rudin, principle of mathematics, mathematical analysis. Okay, so by the end of this class, you should be able to understand and explain why real analysis cannot be built only on rational numbers. And also I will go over the proof of that no rational numbers has the square equals to 2. So basically we're proving the radical 2 is a irrational number. And I want to basically and also the proof of the radical 2 being a rational number will be by contradiction. So I'll talk a little bit about that as well. We will actually go over the full proof. And also we will, so the terminology of in Lois terms, it's also going to be the key to prove the theorem. So let's go over some prerequisite. So the rational numbers A rational number, it's a number which can be written as m over n, where m and n are integers. So z in mathematics stands for the set of integers. So like 0 plus or minus 1 plus or minus 2. So basically it's all whole numbers. And in order for this number to be defined, I want the denominator to be a non-zero integer. And that's why we emphasize that n doesn't equal to 0. And the set of all rational numbers is denoted by the fancy Q here. So for example, 3, it's a rational number because it can be written as the quotient of 3 and 1. For example, negative 5 over 2, it's a rational number since it can be written as the quotient of negative 5 and 2, or 5 and negative 2. And they are all integers. And also 0, it's a rational number because it can be written as the quotient of 0 and 1. And in fact, it can be also 0 and 2, 0 and negative 1. As long as the bottom is an integer, that's going to be fine. And a fraction, it's in lowest terms. If m and n have no common positive integer factor larger than 1. So in other words, there's another saying of that, which is m and n are co-prime. So basically, they don't have any common positive integer factor larger than 1, means that I cannot simplify this fraction anymore. So for example, the 6 over 8 is not in lowest terms because if we look at 6 and the 8 here, I can simplify this by dividing both 6 and 8 by 2, and I shall get 3 over 4. So, and in this case, their common positive integer factor is equal to 2, which is greater than 1. However, the 3 over 4 is in lowest terms because we cannot find a positive integer larger than 1, which is their common factor. So basically, the fraction is in lowest terms means that we cannot simplify this anymore. Okay, let's go over the even integers. So an integer is even if it can be written as 2k for some k in the set of integers. So for example, 1 is an integer, and if I consider 1 times 2, that's going to be 2. And if I consider negative 1, negative 1 times 2, it's going to be negative 2. 0, it's an integer. 0 times 2, it's going to be 0. And you see, these are all the even numbers. So that's a pretty useful definition. A useful fact is that if m squared is an even number, this will indicate that m is even. So I think we're going to use this fact to show that radical 2 is not a rational number. And how do I show this fact? Well, if m squared, so basically in here I'm trying to use a contradiction. Or in other words, we're trying to prove the contra positive of the statement. So basically, let's use the view of contradiction here. So if m were odd, this means that m can be written as some even number plus 1. And because of that, if I consider m squared, and that would be 2k plus 1 squared, and according to the perfect square formula, I shall get 4k squared plus 4k plus 1. And if I factor a 2 out, I should get 2 times 2k squared plus 2k, plus 1. And since we know that k is an integer, then 2k squared plus 2k is also an integer. So basically, m squared can be written as some 2 times an integer plus 1, indicating that this is an odd number. So an odd integer cannot have an even square. If that's the case, then if something square is even, then that thing must be even. And that proves the fact. Okay, so these are all the prerequisites. Let's get to the main lesson. So the first problem is that rational numbers have gaps. So at first, people think that the rational numbers q are large, it's large enough. So I'm going to convince you why the set of rationals are large. And then I'm going to convince you that this kind of large is not enough because it still have gaps. So the reason why Q is large is that between any two rational numbers, I can always find another rational numbers. And if that's the case, if I have two rational numbers A and B here, it is guaranteed that there's another rational C between them. And since A and C are both rationals, it's guaranteed that there's another rational D between them. And since, C and D are rationals, it is guaranteed that we have an rational E between them. So you see, I can do this infinitely, and the set of rational numbers are very clouded. So if I can show that, I think it would be a very, very nice point to show that the set of rational numbers are pretty large. So for example, between 1 and 2, so 1 is a rational number and 2 is another rational number, I can just take their average. So 1 plus 2 divided by 2 is exactly their average, and that's exactly 3 over 2. And since this is already in forms of the quotient of two integers, that's in Q. And also, I can do this more. Between 1 and 3 over 2, I can again take the average, and I shall get 5 over 4. So, as you can see here, for any two rational numbers, A over B and C over D, if I want to find a rational numbers between them, I can just add them together and divide by 2. And I shall get BD, and here's AD plus BC divided by 2, and I shall get AD plus BC over 2BD. And that's a rational number because both A, B, C, D are integers, and which makes this a integer and this a integer. And that's exactly their average, so it should be another rational number between them. Okay, so the rational numbers are pretty clouded. However, being crowded does not mean complete. So I'm going to tell you what complete means later. But for now, we can just say that they have gaps. They can still have missing numbers. So the first major example is the number that should satisfy x squared equals to 2. So geometrically, this number is the diagonal length of the square, which the side length is 1. So let's look at the picture here. So this is a square, and this is the diagonal. And according to the Pythagorean theorem, since this is a right angle, we have 1 squared plus 1 squared, let's call this x, equals to x squared. and this will become x squared equals to 2. So basically, we want to understand that if this length is a rational number, and algebraically, we would like to say this equals to radical 2. And however, we know that the radical 2 doesn't belong to the set of rationals. So the rational numbers have a gap. Well, this is like a common fact from high school, but we haven't proved it thoroughly yet. So maybe it's time to prove that radical 2 is not rational. And before I do that, let's look at the checkpoint. So why does the fact that there are many rational numbers between 1 and 2 not prove that Q has no gaps? So I'm going to let you guys think about that, and I will write the answers in the comments. Okay, so now let's go ahead and prove that radical 2 is not rational by contradiction. So let's introduce the proof by contradiction. So proof by contradiction means that we assume the opposite of what we try to prove to be true. And if that's the case, we can do a lot of logical reasoning from that assumption. And eventually we arrive at something impossible. And if that's impossible, then the original assumption must have been false, indicating that what we are trying to prove is true. So something to keep in mind that is that the opposite here, it has to be the exact opposite. So for example, in this case, if I want to show that 2 is not rational, then I'm going to assume that, well, let's just assume that radical 2 is rational. If I assume that and try to do a lot of stuff and turns out that this is just impossible, then we have derived that radical 2 it's impossible. Oh, sorry, radical 2 is rational, it's impossible. Therefore, I can just conclude that radical 2 is not rational because there are only two possibilities, whether rational or not rational for radical 2. So here it's what we want to prove. There's no rational numbers p such that p squared equals to 2. So basically, if I can show that no rational numbers after I square it, I shall get 2, then the so-called radical 2, it must be not a rational number, because if it is, then this rational number square will become 2. So let's begin by assuming the opposite. There's a rational number p. So we say that, well, let's assume that there is a rational number p such that p squared equals to 2. Okay, so before we start the proof, let's look at the checkpoint 2. So in a proof by contradiction, do we assume that the statement we want or the opposite of the statement we want? So feel free to type your answer in the comments as well. Let's go ahead and go to the proof. So theorem, there's no rational number p such that p squared equals to 2. Okay, so let's use contradiction here. Suppose for contradiction, there's that such a rational number exists. Let's assume that there's a rational number p such that after I square it, I shall get 2. Then since p is rational, I can write p as the quotient of two integers m and n. So m and n belongs to the set of integers. And now, Yes, so m and n are the set of integers and n doesn't equal to 0. And we want to assume um, the key things here. The fraction, it's in lowest terms. So this is the key of the proof. And you guys may wonder why we want to do that. And the reason why we want to do that is that later I'm going to show that the function is not in lowest terms. And that's going to be a contradiction because the function cannot be in lowest terms and not be in lowest terms. That's because that's exactly these two statements are exactly the opposite of each other. So um, and also you guys may wonder that what if the function is not in lowest terms? If I choose some bad m and n, for example, if I want to say that I don't know p equals to 0.1, and in this case maybe a pretty reasonable choice is that p can be written as 1 oh how about 10 over 100. I mean if I do that I can just try to simplify this and make sure that this is in lowest terms, which is 1 over 10. Okay, so basically now we know that p is a rational number which can be written as the 2 coprime m and n. So that's another way to say it. Okay, so since p squared equals to 2, then m over n, so m over n is our p here, m over n squared equals to 2. Therefore, m squared divided by n squared equals to 2. And rearrange the equation for a bit, and I shall get m squared equals to 2n squared. So since n is an integer, let's be careful here, then this will imply that n squared it's also an integer. Therefore, m squared is equal to 2 times some integer m and n squared. So this is an integer. Therefore, by the definition of even numbers, m squared is even. And notice that from the fact that we just proved, if m squared is even, then m is even. So this is the interesting part. If m squared is even, then m is even. And that's going to give us that m is even because we just shown that m squared is even. And since m is even, then by the definition of even numbers again, there must exist some integer k such that m equals to 2 times k. So for example, if m equals to 8, and in this case, k will be 4. So 4 times 2 equals to 8. So m has to equal to some integer times 2. In this case, I'm just going to denote that integer to be k. Okay, so since m equals to 2k now, and we also know that m squared equals to 2n squared, then I can substitute 2k for m, and I shall get 2k squared equals to 2n squared. And if I square the 2k, I shall get 4k squared and equals to 2n squared. And since both sides have some common factor of 2, I can divide both sides by 2, and I shall get 2k squared equals to n squared. And notice that since k is an integer, this indicates that k squared must be an integer as well. Therefore, n squared, it's basically written as 2 times some integer, k squared, indicating that n squared, it's even. And because of the fact, again, if any number squared is even, then that number must be even as well. Therefore, n is even. So we have shown that both m and n are even from the previous process, which means that they are both divisible by 2. And basically, 2, it's going to be their positive common factor. But we just said that the functions it's in lowest terms. So that contradicts. So this is where the contradict. I like to use this symbol for contradiction. This contradicts the fact that m over n was chosen to be in lowest terms. Therefore, our assumption must be false. So no rational numbers has the square equal to 2. And that completes the proof. Okay, so before we go on, let's go over the checkpoint number 3. So what's the contradiction at the end of the proof I just did? Feel free to type it in the comments. Okay, so these are some examples, which indicates that. So this example, it's basically I try to use a rational numbers and try to square it and see if I can get 2. And it turns out that I failed because no rational numbers will do that. So if I choose 7 over 5 and I square it, I shall get 49 over 25. But since 2 can be written as 50 over 25, then they don't equal to each other. However, this is pretty close. It's a pretty decent approximation of radical 2, actually. However, um, it will never be the precise radical 2. Okay, so so I think that covers everything for this video, and I'm going to give you some basic practice questions, and here they are. So please pause the video and try to do them, and also feel free to um, write them type them in the comments. I'll also post the answers in the comments as well. Okay, so here are some common mistakes we have. So I want to emphasize that the set of rational numbers can only approximate some some sort of identities, like for example, the previous example is the radical 2. So we know that 1.414 it's also a rational number, and it's a pretty close number, to be honest, to radical 2, but still, that's not going to be exactly radical 2. And also, we want to understand that the lowest term here is the key here. So the contradiction is that eventually m and n are both even though they were chosen to be the lowest terms. And these two statements contradicts each other. Okay, so and here we say that the rational numbers are, for now, let's forget about the dense here. So it turns out that the definition of dense here have so we have another definition for that. So we're going to show that the rational numbers are dense in a set of reals later. But for now, we can just say that they are pretty crowded because for all the rational numbers, if I choose any two distinct ones, I can always find one between them. Okay, but that doesn't mean the completeness. So basically, they still have gaps. Okay, so I think and um, so how about I just show you guys the answer without write them down in the comments. So when you guys finish the questions, here are the answers. Okay, thank you very much. So this is the first video of the real analysis, and I will see you in the next one. Thank you very much.